verder te houden, te definiëren. En dan wijzen we dat niet van een verrassing komen in december. Indien die regie niet allemaal is. Oké. So I'll continue with the surface coating part, or the deposition part, or where we put basically a layer on a surface by means of a specific process. Now, this is also sort of the transition to the second part of the course, where we'll talk about the thin film aspects. Now, when we talk about a good coating, we can wonder what is a good coating, and in some cases we will put a layer on top of a surface for the electrical performance. So that means that a resistance aspect in case of a metal coating, or a capacitance in case of a dielectric passivation will be important. So coatings can indeed be metallic, semiconducting, or dielectric in nature. In many cases we also rely on a coating that gives good mechanical characteristics, that we have a good conformality, that it have a specific hardness, and that it has a good adhesion. Now, the adhesion is something we can control definitely by the surface pre-treatment first. A coating may also be required to make the surface resistant to the next step. This could be resistant to an etch process. So in this case, we put a photoresist material on top. It should be uniform over the whole area. It should be very reproducible, and cost is in any process an issue. So some of the parameters that are under consideration whenever we talk about depositing coatings relate to the stoichiometry. Do we have the appropriate stoichiometry? If we do silicon dioxide, is it the silicon dioxide layer, or is it the suboxide of the silicon dioxide? The porosity of the material or the layer is often very important. It can be that we require high porosity films, but in some cases we will also consider low porosity materials. I'm not going to specify where and when we need low porosity films. That will be addressed in some of the subsequent classes. There can be impurities in the material which will lead to detrimental effects, but if you're depositing a semiconductor layer, the impurities are wanted, because the impurities will give you the doping of the silicon layer. So an impurity is not always bad, it can be beneficial or even needed. And the key part, whenever you put a coating on a surface, is the interface. You will form an interface between material 1 and material 2, and that is very often the cause of many problems. I mean, electrical performance will suffer, the adhesion will suffer. So interfaces are crucially important. The surface coating processes, I broke them down in the oxidation process, because that's a specific subset whereby we're converting part of the original material into its oxide form. And then we have physical vapor deposition processes and chemical vapor deposition processes. And then I will briefly touch, because there's classes dedicated to epitaxy, and there's a class dedicated to atomic layer deposition. But I'll briefly touch on epitaxy and atomic layer deposition, because these are two nice examples to distinguish on why in some cases we would need an oxygen-free surface, and why in some cases we would need an OH terminated surface. So from the point of view of silicon, here for epitaxy we would an oxide-free surface. From the point of view of silicon, for an ALD process we would need an OH terminated surface. So this links it back to the cleaning steps in the cleaning application. So again, this is what I said in the first slide. This surface is not stable. If we expose it to the ambient, we will have an oxide intersection in between the silicon lattices here, and we will have an OH termination being formed. We typically call this a native oxide or a chemical oxide. It's a slow process because you can see here, this is the amount of oxide that is being formed, or the thickness of the oxide in the order of nanometer here, or 1 nanometer here, so sub 1 nanometer here, as a function of time. So it is an unstable surface, but it is a relatively slow process. Why? Among others, because oxidation is determined by the concentration, is determined by the temperature. So at ambient room temperature with ambient concentrations of oxygen in the air, it is a slow process, but what you need to remember here is that if you would leave a surface exposed, you will have a chemical oxide being formed, or a native oxide being formed on the silicon surface, and the thickness is typically in the order of 1 nanometer, as a rule of thumb by process. Now, in many cases, we need a thicker oxide. We need an oxide in the order of several tens of nanometers formed on the silicon surface. And in those cases, we will use a thermal process, so we'll use high temperature to achieve this oxidation process. Now we distinguish here between a dry process, which is the silicon exposed to oxygen vapor, or a wet process, the silicon exposed to water vapor. And in both cases, the end product is an SiO2 layer. You've seen this image on the first slide. So this is the crystalline structure of a silicon wafer, on which we start to do an oxidation process. And this, well, shady area here is basically the SiO2 that is formed on the silicon. Now, in order to form the SiO2, we need to consume silicon. And that is what I'm trying to explain here. So this is the bulk material, this is this area here. This grayish area is that area which is intersected by the red line here. And this is the dashed line is representative to the red line here. If we start to do an oxidation process, the oxidizing compound arrives at the surface and will convert the silicon. Now, in order to convert the silicon, it will basically have to diffuse through this oxide layer and undergo a surface reaction here. If it undergoes a surface reaction, silicon plus oxygen, there's a volume expansion. So the material grows above and below the original surface. So with an oxidation process, we basically will have oxidizing species diffusing over the oxide barrier, reacting at an interface that is gradually going deeper and deeper into the substrate, resulting in a layer that is being formed on top. And the conversion rate is typically that you would actually consume about 45% of your silicon substrate to make 100% of an oxide thick layer. So you have an expansion and a diffusion over a process. It's an amorphous layer, so contrary to quartz, which has a crystalline ordering, the silicon dioxide that is achieved by thermal oxidation or by chemical oxidation on the surface will result in a amorphous structure, so there's no long-range order present in that surface. I mean, for the experts, you can see this. Here you have the nice crystal lattice, so the silicon atoms align here, and here you have an amorphous or a more random structure. There's a little bit more information here. The density of such an amorphous layer is less than the density of quartz. There's some other properties here, but important to realize is that you will always have within that matrix also those silanol groups, so the hydroxylated groups, not only present at the surface but also in the bulk of the material, depending on the density of the oxide that you form. Now, what I would like to come to is this specific case of oxidation, of thermal oxidation, that is described by Bruce Deal and Andy Grove. Two names that may sound familiar. Yes, these are the two people that were involved in the founding of Intel. But before they became rich with the company, they also worked as scientists, and they developed a model for oxidation. Why was this so important for them? Because the heart of a transistor is basically oxidized silicon dioxide, or at least until a few generations ago it was oxidized silicon. So understanding how the silicon substrate was converted into a high quality silicon oxide was important for them, and that's why they devoted a lot of time and effort on understanding and coming up with a model that describes the thermal oxidation of silicon, at least for thicknesses above 10 nanometers roughly. It is again a process of three terms. You have a conversion or a transport of gaseous oxidizing compounds from the gas to the interface of the oxide that is being grown. Then you have a conversion from gaseous compounds at the interface to dissolved oxidized species in the oxide. You have a diffusion of the oxidizing species over a diffusion layer, and you have a surface reaction here. Very similar to the three steps that we described in the cleaning step. You have a surface reaction, you have a diffusion over a boundary layer, and you have a transport in the bulk, in this case, of the gas. So three compounds, a flux 1 gas species going to the surface, diffusion of the oxidizing species over the growing oxide, and a surface reaction. There's a little bit more explanation here, but the first flux are the oxidizing species from the bulk of the gas phase to the gas-oxide interface. That flux can be described as a mass transfer coefficient and the difference in gas phase concentration and surface concentration. For this particular derivation, they do a conversion to make sure that it's expressed in the same units. They use the ideal gas law and Henry's coefficient to convert this from a gas concentration, surface concentration, to again, a bulk concentration and a surface in the oxide that can basically diffuse. There's a little conversion of the mass transfer coefficient, which now goes into a factor H. The conversion is basically described here, but it's nothing more than using the ideal gas law and putting all of the constant terms plus the temperature in the new defined H factor. But for the sake of understanding of the process, there's a first flux that transports the oxidizing species from the gas phase to the interface. There's a second flux, which is described by a diffusion law, the diffusion of the species over the growing oxide. So there's a diffusion constant and a concentration gradient over the growing oxide. That's your second term here. And then the third term is basically a reaction rate determined flux the speed at which the species react away at the surface, described in a first order chemical equation. Now if you reconvert all of those terms and you assume that under steady state conditions there's a balance between the flux 1, flux 2 and flux 3, then you can basically rework this equation into what is called the Deal growth equation, and it's a quadratic description of how the oxidation process happens. So there's the oxide thickness is the quadratic term, and there's a constant factor A and B that is being described, and then a factor T, the time, because indeed the longer it takes or the more time you have, the higher or the thicker the oxide will grow. And there's a factor tau, which is an offset for the initial oxide that is present. So you may have some oxide present on the surface when you start the process, and that gives the time offset, because it would have taken a certain amount of time to grow that initial oxide. Now, I'm just going to go immediately to this slide. So you have the quadratic equation here, and you have a description for what the A, the B, and the tau term would be. Now, what is important in the oxidation process is to understand that there's high order two limiting situations. You have a long time situation and you have a very short time situation. If you work at relatively long time, you will have a thick oxide present on the surface, and the time is long compared to the initial offset, and the quadratic term will dominate over the linear term here. So you can basically say that at long time it's a quadratic expression, and you have B or beta or B being defined as the parabolic rate constant. Now if you look at B, it is, besides of the concentration and the unit volume, it is depending on the diffusion constant. So at high or long times, the oxidation process becomes diffusion limited. That is, if the oxide is so thick, it takes a long time before the species can basically diffuse through that growing oxide, and whatever species makes it to the interface with the silicon will react away. But it's the diffusion that limits the process, and that's why you have a leveling off, that's why you have the parabolic growth. For very short times, the equation can be written like that, and it's controlled by the B over A factor, which is the linear rate constant. Now if you write B over A, then the diffusion basically disappears from this, and the reaction rate constant, so the speed of reaction at the interface, remains as the determining factor. So at short oxidation times, everything, it's the reaction rate, the speed at which the species can react away, that determines the growth of the oxide. So it's a reaction rate limited, and in the initial phase it is a linear growth, and then it starts leveling off to a parabolic growth. That is what you would see in this graph here. So this is at relatively short time, it's a linear growth, and at longer growth times it converts into a parabolic growth. So two limiting cases, one that is controlled by the reaction rate, that's the second one here, and one that is controlled by the diffusion. So process 2 is in the initial phase, process 1 is at longer times. Now, I'm not going to give you more details on this process, other than two specific examples on where differences in the oxidation process come into play. In this figure here, they have the inverse of temperature, and they have here the parabolic rate constant plotted for two types of oxidation. So what I described as the dry oxidation and what I described as the wet oxidation. Now, whenever you make a plot of an entity as a function of the inverse of the temperature, the slope is the activation energy. And what we see here is that there's a difference in activation energy for the two types of oxidation processes. And the reason, so a dry oxidation has a higher activation energy for diffusion than the wet oxidation process. And the reason for this is that the water molecule is smaller than the oxygen molecule, so it can diffuse easier through the formed oxide. So the diffusion is easier than the diffusion of water. Therefore, for the parabolic growth part, you have a difference in activation energy. Now, if we look at the linear rate constant, we see that the same. In this case, we have the inverse of the temperature, and now we have the B over A factor plotted here, and we see the same slope for the dry oxidation and the wet oxidation, meaning that there's almost the same activation energy on whether we bring the silicon surface in contact with oxygen or with water at the initial stages of the growth. And why is that? Because it is in this case not the oxidizing compound, but it is the energy required to break the silicon lattice. So we have a silicon-silicon bond, which you have to break to do the initial oxidation. That's the reaction that has to happen. And that does not depend on the species that you use to oxidize, but that depends on the energy needed to break that bond. That is why the activation energy is the same in those cases. Here you see, and that's just for information purposes, but you see the effect for wet oxidation and for dry oxidation, the effect of temperature on the A and B parameter. And one thing here, what you see here is two crystal orientations, so the 100 and the 111 orientation. And you will see that the reaction rate, so this term here, the activation energy, is different for a different crystal orientation. And the reason for that is that in one case, you have a higher number of silicon atoms and silicon bonds present than in the other case. So obviously the activation energy depends on the number of bonds that need to be broken, and that is higher for the silicon 111 than for the silicon 100. So that's what you have to remember from the oxidation process, that there's a model describing the oxidation process for thicknesses 10 nanometers and above, which is determined by a linear component in the initial process, and which is controlled by a parabolic component for longer oxidation times. The longer component is because of the diffusion, the linear component is because of the reaction rate at the surface. Now the last two things that I will discuss on surface coating is just give you some quick impressions on why we need a hydrogen terminated surface and why we would need an OH terminated surface, depending on which type of deposition process we execute. Both on epitaxy and on atomic layer deposition, there will be extensive classes by my colleague Professor Delaby. So I'm not going to shave the grass in front of her feet, but just going to show a few slides here to make the point that the surface preparation is crucially important. Now, epitaxy comes from the Greek word upon and arranging. So it is what we're doing in an epitaxial process. We're going to deposit a material in its crystalline form, and we can do that only if we have a crystalline template underneath. And the idea of the epitaxy process is that the ordering of the crystalline material on which you do the deposition is continued in the growing layer. So you basically do a template matching. You have a crystalline structure, you put something on top by a physical or a chemical process, and you have a continuity of the crystalline lattice with some concerns in some cases. In order to have a good epitaxy process, you need to be able to see the crystalline structure underneath. And if you have an oxide on the surface, I told you earlier, if you have an oxide on the surface, you have an amorphous character. So there's no crystalline order. So you will not be able to have a crystallinity continuity on top of the oxide. You can still deposit a crystalline structure, but it will be polycrystalline. It will not be single crystalline. And there should be a lattice matching, because if the lattice here is completely different from the material that you grow on top, then obviously you will have defects and defectivity here at this interface. Here you see the simplest example. So if you do silicon epitaxy by using a chemical vapor deposition process, so silane, which will thermally decompose on the surface, leaving silicon and desorbing hydrogen, done at temperatures above 500 degrees C. You can see here what is happening here, and this red box is magnified here. Here, in this part, we had a hydrogen-terminated surface. So where silicon atoms are arriving on this crystalline matrix and they follow the order. So you have a nice continuity of the crystalline order going up. Here, the light dashed area is oxygen that is present, so an amorphous nature. And the silicon atoms will still deposit, they will crystallize, but you see facets here indicating that you have different crystal grain orientations. Here it is the same single crystal process that is continued, so you will not be able to distinguish between the crystal here and the crystal here. Here you will have a polycrystalline nature, and that is typically what happens if you nucleate on an amorphous outer layer. It will be polycrystallinity. If you want to have that silicon epitaxy, then you need to have a nice oxide-free surface. This is in case of silicon on silicon. So if you put silicon on silicon, then obviously the crystalline lattice here and the crystalline lattice here is the same. So you will have a good continuity. They call this homoepitaxy. In some cases, you will also have a different material deposited on a crystalline lattice. For example, germanium or silicon germanium. Now, the lattice parameters are different. So if you want to match a larger crystal on a smaller crystal, you will have strain. So you will have indeed a lattice matching, but whenever there is strain, whenever there is tension here, you can have dislocations and you can have defects. But that will be discussed more by colleague Delaby in her session. And then just one way, here you see one way of overcoming that strain is by introducing a buffer layer with a matching lattice parameter. So you have silicon, and we're just going to put strontium titanate on top of the silicon. So the difference between the silicon lattice parameter and the strontium titanate lattice parameter is small. So we'll have a little bit of strain, but manageable. And then we put barium titanate on top, which has a small gap between the lattice parameter of strontium titanate and barium titanate, which is again causing a little bit of strain here, but manageable. If we would do the barium titanate immediately on the silicon, then we would have a lot of defects, a lot of dislocations, a lot of problems there. And then the other example, and I think, in this case it may be a little better to use the animation for that. So is an atomic layer deposition process. And atomic layer deposition is again something that you've probably done in your childhood, making these type of sand paintings, whereby you wanted to create this colorful image. And what did you do, or how did you approach this? Well, you made your drawing first. So that's your pattern substrate. And then you applied some glue on part of the surface. So you created reactive sites. And then you did put on some colored sand. And obviously the colored sand remained at the places that were activated, that were glued. So you were creating the shape of the dolphin in there. And then you basically flipped the painting over, and all of the non-reacted sand basically fell off, and you had a very nice exposure of the dolphin image. Well, this is what atomic layer deposition is also doing, but then in a chemical way. I mean, you can then continue with other colors, and then you have that very nice image, or at least, I mean, it depends on how good you're in drawing and in gluing, but the same is true for atomic layer deposition. So you basically have two precursors and a surface. And I have my surface, and I allow precursor 1 to come in, and precursor 1 will react with the surface. So that's the glue part. Only where my surface is activated, my precursor will react. So there will be a chemical reaction between the precursor and the surface. Then I have this stage of flipping the paper. So whatever sand that did not react falls off. Well, the same is true. I'll just have a neutral gas purging all of the non-reactant precursor away. In an ideal situation, I end up with a situation where all of the activated surface is now occupied by precursor 1. And then I bring in a second precursor, which will convert this adsorbed precursor 1 into a new activated surface. And again, I do a purge. So I wash out all of the non-reacted precursor B, and I have a first atomic layer being deposited. There's quite some tricks behind this, but the process is I would use an aluminum containing precursor which would react with an OH surface, and then I will use a water or an oxidizing species to rehydrolyze the aluminum, and then I'll have again my aluminum precursor and hydrolyze, and aluminum precursor and hydrolyze. So this is what is basically happening, and we can see that depending on the amount of surface sites, I will have a full occupation. If there is no reactive site, I cannot react. If there is a reactive site, it can react. This is where the cleaning comes in. The ALD process works well on OH groups. If you have OH groups on the surface, most of the precursors will react with that surface, and you will have the conversion to the reactive site. There's a complication that the precursor may be too bulky, and that you don't have a full monolayer coverage because of a bulky ligand or because of too few reaction sites. But it's more important to understand, and this will take us too far, but this is an important one. You can have a variety of growth processes. In the first case, so you have a limited nucleation, but then in the second cycle of two processes, you fill in the empty spaces. So you basically, the surface reactivity is higher than the reactivity of the deposited layers. And only if the surface is fully covered, you will have the second layer being grown. This is truly monolayer by monolayer growth. In most cases, you will have a situation like this, whereby you have a partial absorption on the surface. You convert this surface and make it susceptible to an absorption of the second precursor, and you have sort of a hybrid growth whereby the film gradually closes, but you don't have a first fully closed layer before the second layer is closed. But all this is depending on the surface termination. Now, if you have a surface with without any OH group, so in particular an hydrogen terminated surface, then you may have one nucleation site, and this surface is more reactive than the neighboring surface, so you will have an island-like growth and a pore growth. So that as the two examples for where you need an OH terminated surface and where you would need a hydrogen terminated surface. And then a short connection to last two classes. A lot of the characterization techniques that were described in the last two classes are being used to the characterization of surfaces and thin films. So contact angle measurements allow you to do an assessment of the hydrophilicity, the hydrophobicity. Cyclic voltammetry can tell you something about the goodness of passivation, how close is your surface. Infrared gives you information on the chemical groups. The time of flight, secondary ion mass spectrometry or secondary ion mass spectrometry alone gives you information on the chemical composition and the layer closeness. Raman gives you also, like infrared, information on the chemical groups. Zeta potential measurements will tell you something about surface charge. And then we go into techniques that tell you more about the layer thickness. So the ellipsometry, X-ray diffraction, X-ray photoelectrospectroscopy give you. So there's some information here. This is a slide that you've seen I think in the presentation of my colleague Caroline Jans. So I'm not going to repeat that, but there's just two techniques, or at least one technique that I would like to highlight here, because I'm pretty sure that she did not touch on that one. And that is a technique that is called light scattering. And this is a concept that is used to identify particles on a surface. So the pie-shaped segment is just a segment from a wafer. It operates on full wafers, but this is just for the graphical representation. And from the top, you're basically shining a laser on top of the surface. The surface is reflecting, so the laser beam will basically scatter from the surface, and we are measuring both in plane and perpendicular to the plane. So whenever it's a shiny surface with no particle or no defect on the surface, the light will reflect in the two components in a specific direction. Now if there's a particle on the surface or a pit in the surface, but let's consider a particle for now, the laser will hit that particle and the light will scatter in a different direction than when it reflects from a mirror-like silicon surface. So we will measure a different component in plane and a different component in the perpendicular direction. By correlating this to the